You must prepare the raw data you're using to transform prior to fitting your machine learning model. This is required to ensure that you expose the best structure for your predictive modeling problem to the machine learning models. Applying data transforms like scaling and encoding categorical variables is straightforward when all the input variables are the same type. It can be challenging when you have a dataset with mixed types, and you want to selectively apply data transforms to some, but not all of the input features. Thankfully, the scikit-learn Python machine learning library provides the column transformer that allows you to selectively apply data transforms to different columns in your dataset. In this lesson, and the next few, you're going to discover how to use the column transfer to selectively apply data transforms to columns in your dataset with mixed types of data. It's important to prepare data prior to modeling. This may involve replacing missing values, scaling numerical values, and one-hot encoding categorical data. Data transforms can be performed using the scikit-learn library. For example, the simple emitter class can be used to replace missing values, the min-max scalar class can be used to scale numerical values, and the one-hot encoder can be used to encode categorical variables. Sequences of different transforms can also be chained together using the pipeline, such as emuting missing values and then scaling numerical variables. It's very common to want to perform different data preparation techniques on different columns in your data. For example, you may want to emute missing numerical values with a median value, and then next emute missing categorical values using the most frequent value, and then one-hot encode those categories. Traditionally, this will require you to separate the numerical and categorical data and then manually apply the transforms to those groups prior to combining the columns back together in order to fit and evaluate your model. Now, you can use the column transformer to perform this operation. The column transformer is a class in the scikit-learn Python machine learning library that allows you to selectively apply data preparation transforms. For example, it allows you to apply a specific transform or a sequence of transforms to just the numerical columns, and then separate the sequence of transforms to just categorical columns. In order to use the column transformer, you must specify a list of transforms. Each transformer has 3 element tuples that define the name of the transformer, the transform to apply, and the column indices to apply it to. For example, the columnar transform on screen applies the one-hot encoder to column 0 and 1. The example on screen applies the simple emitter for numerical columns 0 and 1. The simple emitter with most frequent emuting to categorical columns 2 and 3. Any columns not specified in the list of transformers are dropped from the dataset by default. This can be changed by setting the remainder argument. Setting remainder to pass through will mean that the columns are not specified in the list of the transformers will be passed through without the transformation, instead of being dropped. For example, if 0 and 1 columns were numerical and columns 2 and 3 were categorical, and we wanted to just transform the categorical data and pass through the numerical columns unchanged, we could define a columnar transformation as shown on screen. Once the transformer is defined, it can be used to transform the dataset. A column transformer can also be used in the pipeline to selectively prepare the columns for your dataset before fitting the model in the transformed data. This is the most likely use case. It ensures the transforms are performed automatically on the raw dataset when fitting the model, and then when making predictions, such as when evaluating the model in the test dataset via cross-validation, or making predictions on the new data in the future. Alright, now that we're familiar with how to configure the column transformer in general, in the next lesson we're going to work through an example. Alright, in this lesson we're going to work with a new dataset. The abalone dataset is a standard machine learning problem that involves predicting the age of an abalone given measurements of the abalone. The dataset has 4,177 examples, 8 input variables, and the target variable is an integer. A naive model can achieve a mean absolute error of around 2.363% by predicting the mean value, evaluated via tenfold cross-validation. When we output the columns, you can see the first column is categorical, and the remainder of the columns are numerical. You may want to one-hot encode the first column and normalize the remaining numerical columns. This can be achieved using the columnar transformer. You can model this as a regression predictive modeling problem with a support vector machine model. First, like always, we need to load the dataset. We can load the dataset directly from the file using the readcsv pandas function. Then we're going to split the data into 2 data frames, one for input and one for output, the complete example shown on screen. When we execute the code, you can see the dataset is properly loaded and split into 8 input columns and 1 target variable. Next, we can use the select_dtypes function to select the column indices that match the different data types. You're interested in a list of columns that are numerical columns marked by a float 64 or N64 in pandas, and a list of categorical columns marked as an object or bool type in pandas. You can then use these lists in the column transformer to one-hot encode the categorical variables, which should be just the first column. You can also use the list of numerical columns to normalize the remaining data. Next, we're going to define an SVR model, and then define a pipeline that uses the first column to transform, then fits the model in the prepared dataset. Finally, we can evaluate the model using tenfold cross-validation and calculate the mean absolute error, averaged across all evaluations of the pipeline. When we run our example, it evaluates the data preparation using tenfold cross-validation. In this example, you achieve an average MAE of about 1.4, which is better than the baseline score of 2.3. You now have a template for using the common transformer on a dataset with mixed data types that you can use and adapt to your own projects in the future. As you surely know by now, data preparation is a big part of applied machine learning. Correctly preparing your training data can mean the difference between a mediocre and extraordinary results, even with very simple linear algorithms. Performing data preparation operations, such as scaling, is relatively straightforward for input variables, and it's been made routine in Python via the pipeline scikit-learn class. On regression predictive modeling problems where the numerical value must be predicted, it can be critical to scale and perform other transformations on the target variable. This can be achieved in Python using the transform to target regressor class. Scaling input variables is pretty straightforward. In scikit-learn, you can scale objects manually or with a convenient pipeline that allows you to chain a series of data transformation objects together before using the model. The pipeline will fit and scale the objects on the training data for you and apply the transforms to the new data, such as when using a model to make predictions. The challenge is, what is the equivalent mechanism for target variables in the scikit-learn library? There are two ways you can scale your target variables. The first is to manually manage the transform, and the second is to use a new automatic way of managing the transform. Manually managing or scaling the target variables involves creating and applying the scaling object to the data manually. It involves the following steps. Number 1, you create the transform, for example, a min-max scaler. Number 2, you fit the transform in the training dataset. Number 3, you apply the transform to the training and test datasets. And then number 4, you invert the transform on the predictions made. For example, if you want to normalize a target variable, you would first define and then train the min-max scalar object. You would then transform the train and test target variable. Then you would fit it on the model and use the model to make predictions. Before the predictions can be used or evaluated with an error metric, you would need to invert the transform. Now this can be a pain, as it means you cannot use convenience functions in scikit-learn, such as cross-val scores, to quickly evaluate your model. All right, let's take a look at an alternative approach to automatically managing the transform and inverse transform. Automatic transformation of the target variable can be achieved by using the transform target regressor object that wraps a given model with a scaling object. It will prepare the transform on the target variable using the same training data used to fit the model, and then apply the inverse transform on any new data provided when calling the fit function, returning predictions in the correct scale. To use the transform target regressor, it is defined by specifying the model and the transform object to use on the target, as shown on screen. Later, the transform target regressor instance can then be fit on the model by calling the fit function, and used to make predictions by calling the predict function, again as shown on screen. This is much easier and allows for helpful functions like cross-val score to evaluate your model. All right, now that you're familiar with the transform target regressor, let's look at an example using a real data set. We're going to use the Boston housing regression problem that has 13 inputs and 1 numerical target and requires learning the relationships between suburb characteristics of housing prices. The dataset was introduced earlier in the course, so you should have it in your directory. Our example on screen shows how to summarize the dataset and load the data. When we execute the code, it prints the shape of the input and output parts of the dataset, showing 13 input variables, an output variable, and 500 rows of data. Rows are also called observations. We can now prepare an example of using the transform target regressor. A naive regression model that predicts the mean of a target problem can achieve a mean absolute error of around 6.659%. We're going to aim to do better than that. In this example, you're going to fit a Huber regressor class, a type of linear regression robust to outliers, and then normalize the input variables using the pipeline. Next, you're going to define the transform target regressor instance, and then set the regressor to a pipeline and the transformer to an instance of the min-max scalar object. You can evaluate the model with normalization of the input and output variables using repeated tenfold cross-validation with 3 repeats. You tie all this together, our code's listed on screen. When you execute the code, it evaluates the model with normalization of the input and output variables. In this case, you achieved the MAE of around 3.2, much better than the naive model achieved of 6.6. Now, you're not restricted to scaling objects. For example, you can explore using other data transform on the target variable, such as a power transformer. That can make each variable more Gaussian-like using the Yeo-Johnson transform, and improve the performance of the linear models. By default, the power transformer also performs the standardization of each variable after performing the transform. It can also help to scale the ranges from 0 to 1 prior to applying the power transform to avoid problems inverting the transform. You can achieve this by using min-max scaler and defining a positive range, introduced earlier in the course. The complete example of using the power transform on the input and target variables for the housing dataset is on screen. When you execute the code, it evaluates the model with a power transform of the input and output variables. In this case, you can see we have a further improvement to the MEE of about 2.9. It's critical that any data preparation performed on a training dataset is also performed on the new dataset in the future. This may include a test dataset when evaluating a model, or new data from the domain when using the model to make predictions. Typically, the model is fit on the training dataset and saved for later. The correct solution to preparing new data for the model in the future is also to save any data preparation objects, like data scaling methods, to a file along with the model. Each input variable in a dataset may have different units. For example, one variable may be in inches, another in miles, another in days, and so on. Therefore, it's often important to scale the data prior to fitting it to modeling. This is particularly important for models that use a weighted sum of the input or distance measures like logistic regression, neural networks, and k-nearest neighbors. This is because variables with larger values or ranges may dominate or wash out the effects of variables with smaller values or ranges. Scaling techniques such as normalization and standardization have the effect of transforming the distribution of each input variable to the same, such as the same minimum and maximum in the case of normalization, or the same mean or standard deviation in the case of standardization. A scaling technique must be fit, which just means it needs to calculate coefficients from data, such as an observed min and max, or an observed mean or standard deviation. These values can also be set by domain experts. The best practice when scaling techniques for evaluating a model is to fit them on the training dataset and then apply them to the training and testing sets. Or, when you're working with a final model, to fit the scaling method on the training dataset and apply the transform to the training dataset and any new dataset in the future. It's critical that any data preparation or transform applied to the training dataset is also applied to the test on other datasets in the future. Now, this is pretty straightforward when all the data and model are in memory. This is challenging when a model is saved for later use. What is the best practice to scale data when saving a model for later use, such as a final model? The solution is to save the data preparation object to the file along with the model. For example, it is common to use the Pickle framework, which is a Python framework, for saving machine learning models for later use, such as saving a final model. This same framework can be used to save objects that are going to be used later for data preparation. The model and the data preparation object can be loaded and used. It's convenient to save the entire objects to file, such as a model object and a data preparation object. Therefore, experts may prefer to save just the model parameters to file, and then load them later and set them into a new model object. This approach can be used with the coefficients used for scaling the data, such as min-max values for each variable, or the mean and standard deviation for each variable. The choice of which approach is appropriate for your project is up to you, but I'd recommend saving the model and the data preparation objects to a file directly for later use. Alright, let's work through an example of saving our data preparation steps. The first thing we need to do is define a dataset. We're going to use a contrived dataset, specifically a binary classification problem with two input variables created randomly via the makeBlobs function. The example on screen creates a test dataset with 100 examples, two input features, two class labels, 0 and 1. The dataset is then split into training and testing sets, and then the min and max values of each variable are reported. Importantly, the random state is set when creating the dataset and when splitting the data, so that the last dataset is created and the same split of the data is performed each time the code is executed. When we execute the example, it reports the min and max values for each variable in both the training and testing sets. We can see that each variable has a different scale, and that the scales differ between training and testing sets. This is a realistic scenario we may encounter with a real dataset. Alright, so let's go ahead and scale the dataset. We're going to use the min-max to scale each input variable to a range of 0 to 1. The best practice use of this scaler is to fit it on the training dataset, and then apply the transform to the training dataset and other datasets, and in this case, the test dataset. The complete example of scaling the data and summarizing the effects is listed on screen. Running the code first prints out the effects of the scaled data, showing the min and max values for each variable in the training and testing sets, We can see that all the variables in both datasets now have the values in the desired range from 0 to 1. Next, let's go ahead and fit the model in the training dataset and save both the model and the scalar object to file. In this example, we're going to use a logistic regression model because the problem is a simple binary classification task. The training dataset is scaled before, and in this case, we're going to assume the test dataset is not currently available. Once it's scaled, the dataset is used to fit the logistic regression model. Next, we're going to use the pickle framework to save the logistic regression model to a file, and the min-max scalar to another file. The example is shown on screen. Running the code first scales the data, fits the model, and then saves the model and scalar to files using pickle. You should now have two files in your current working directory, the model.pickle and the scalar.pickle. Lastly, let's go ahead and load the model and the scalar object and to make use of them. In this case, we're going to assume that the training dataset is not available, and then only new data on the test dataset is available. You're going to load the model and the scalar. Then you're going to use the scalar to prepare the new data, and then use the model to make predictions. Because it is a test dataset, you've calculated the target variables, so we're going to compare the predictions to the expected target variable, and then calculate the accuracy of the model. The complete example is listed on screen. Running the code loads the model and the scalar, then uses the scalar to prepare the test dataset correctly for the model, beating the expectations of the model when it was trained. In order to confirm the scalar is having the desired effect, you report the min and max value for each input feature, both before and after the scaling. The model then makes a prediction for the examples in the test set, and a classification accuracy is calculated. In our example, as expected, the data is correctly normalized and the model achieved 100% accuracy on the test set because the test problem is trivial. This example provides a template that you can use to save both model and scalar objects for your own projects.